The fact that the partial derivative of f with respect to x is itself a function of x and y means that to this function we can apply partial derivatives again. And this gives rise to the concept of higher order partial derivatives. Okay, so this is very simple. We can get the partial of f with respect to x, and to this result we can apply again the partial with respect to x. Okay, in other words, we are doing the partial with respect to x of this new function f subscript x, which is a function of x and y. Okay, and this function is usually written as f subscript x subscript x. So we put two x's to indicate that we have done a double partial derivative with respect to x. Okay, and this is still a function of x and y. Alternatively, this is also written as partial squared of f with respect to x squared. Okay, so this is all very similar to what you knew from one-dimensional derivatives, where you usually used f prime x or f prime prime to denote the second derivative, and so on. But the interesting thing here is that we have two variables. So the same that we do the partial with respect to x, we can do it with respect to y. So the partial with respect to y of the partial of f with respect to y is equal to the partial with respect to y of f sub y, which is a function of x and y, which is written as fyy, which is itself a function of x and y. Or it's written as partial squared f with respect to y squared. But even more interestingly, we can now mix the variables. Okay, so for example, we can do the partial with respect to x of the function which is the partial of f with respect to y, right? So this is doing the partial derivative with respect to x of fy, which is a function of x and y. Okay, remember, fy is a function of x and y both. Therefore, we can do the partial derivative with respect to x. Okay, and this is normally written as f sub xy of xy, and it can also be written as partial squared f partial x partial y. Okay, and finally there is a final combination for second order partial derivative, which would be the partial with respect to y of the partial of f with respect to x. So everything is identical as before, and this would be fyx of xy. Okay, now very interestingly, these are the four possible second order partial differentiations or partial derivatives of a two-dimensional function. But funnily enough, these two are the same. At least they are the same if the functions are continuous. So let me write it down. If fxy, which is a function of x and y, and fyx, which is a function of x and y, are continuous, which means that they don't have jumps, then fxy equals fyx. This is a very interesting property, and if you want to know why this is, I point you to my PDF notes. I give some quick explanation, and also I give even links to internet pages where they explain it graphically and visually. Okay, but it's very interesting to note that the second order partial derivatives with respect to x and then with respect to y is the same as doing it first with respect to y and then with respect to x. And in the following we are going to do examples and we will check that this is true. So see you in the following video. Oh, maybe one last thing before ending the video. This would be the second order partial derivatives, right? So I could write this as second order. But of course, you can also have third order, fourth order, fifth order, and the combinations become more and more and more.